Okay, so we've been doing sequencing of distillation columns, and the previous work was particularly to do with the sequencing of ordinary distillation columns. And we did a whole lot of the 6 heuristics that we could use to sequence azeotropic distillation columns. Sequence ordinary distillation columns. But many mixtures are azeotropic, and for that reason we must learn the tools to sequence azeotropic distillation columns. We will do a little bit, in this lecture we will be doing binary azeotropes, but it is much more powerful to do to be able to analyze ternary azeotropes, and for that we will use residue curves. And what I will require of you is to understand a residue curve diagram and be able to design a distillation train based on the information that you will be getting from a residue curve diagram. But let's start off on binary distillation, binary azeotropes for starters. Okay, so just like the heuristics that we did, those 6 heuristics we did for ordinary distillation, we are still in this phase. Let me get a pointer. We're still in this phase, detailed process synthesis, algorithmic methods, and we are still in separation train synthesis, which allows us to create a process flow sheet. So CPS 410, the aim of CPS 410 is to do all of the tasks necessary to arrive at a process flow diagram. And so this is the aim of what we want to achieve in CPS 410. Okay, so separation sequences are complicated by the presence of azeotropes. And azeotropes are often formed when you have mixtures of oxygenated organic compounds. So the oxygenated compounds, alcohols, ketones, ethers, acids, and water. That will very often involve water. And one of the most common azeotropes that we know is the water ethanol azeotrope, which occurs at about 96% alcohol, 4% water. Okay, in these cases, distillation boundaries limit the product compositions in a column to lie within a bounded region. So if we think of the ethanol water distillation in the azeotrope, it means that if we have ethanol 50%, water 50%, we can distill that right until a high ethanol, a maximum ethanol concentration of 96%. And that means is at 96%, if you boil a mixture that has 96% ethanol and 4% water, what the vapor that comes off when you boil that has got exactly the same composition, and therefore no separation occurs when you do that distillation. So prevent the removal of certain species in high concentrations. So that is ethanol we won't be able to get as 100% ethanol. Okay, I've mentioned that we will be using ternary diagrams. With ternary diagrams, whether you plot species A, B, C on a molar or mass basis, a straight line will determine a mass balance. So let's have a look at this example where we've got component I and component K, or not component, they are streams I and K, which which have 3 components in them each. So I can be shown on this diagram as a mixture of A, B, and C, and K can be shown on this diagram as a mixture of also A, B, and C. When you mix them together, the lever rule says that the mixture must lie on a straight line drawn between I and K. And the amount of K is proportional to the distance from I to M, and the amount of I that went in is proportional to the distance from M to K. So you can see the point M is closer to I, which means that there's more I that went into that, there's more I than K that went into that mixture, because the M has got a composition closer to I than it is to K. When you do distillation, you'll start off with a certain mixture M, and you separate it into a distillate and a bottoms product. So we start at M, and then we will have I and K on exactly the same straight line. And that is a really important point. So this is a mass balance. What we have there from I to K is a mass balance that we get to represent on our ternary diagrams. Right, I have mentioned how important it is to understand how to plot on a ternary diagram. So let's look at water over here, and anything that's plotted in this area here means it's mainly water. So that is 100% water, and therefore lines that are parallel, that are equidistant from this point here at the end. That line, or this line over here, anywhere along this line represents 90% water. So remember that all of these lines that are traveling, that are drawn upwards in that direction, represent an equal amount of water, and therefore these numbers at the bottom, because it starts at 1 over here and it gets less the further away you move from the H2O, it means that these refer to H2O. And the direction must be in such a way that if you take this red line, this line is equidistant from this point over here. So it's a line equidistant from the water. So similarly, dTBP, that's 100%. So we're not going to use this axis because that's only 10%. We must use this axis which says there's 90%. We must use a line that runs equidistant from that point. So these lines that run horizontally are the fraction of dTBP. And so there, 0.65 dTBP is along this horizontal line that runs across there. So if you've got a mixture that is 15% water, 65% dTBP, it's going to lie at the intersection of that horizontal line and this water line that we've talked about previously. That intersection will always represent the rest of the TBA. So the numbers will always work out. If you take 0.65 plus 0.15, we get 0.8, and therefore 1 minus 0.8 is the rest, which is the TBA. Again, we can take TBA the lines that run upwards this way, or let's take this line, a line that runs equidistant from that point where it is TBA. One of these this line yeah, I got that comment. Oh, I see. So you don't have these ternary diagrams at all in the class notes? Ah, okay. I know that in my PowerPoint, it referred to these as the actual the title was wrong. It talked about not ternary diagrams, but it talked about three-phase diagrams, and these are not three phases. What we're talking about over here are the same phase. It's one liquid phase. It's just mixtures. So ternary diagrams is a better description. But you say that you don't have these diagrams at all. Okay. All right. Well, I'll publish the new class notes then that include these diagrams. All right. Let's move on to the next one. Very similar. We're not talking about the actual residue curves yet, but these black lines are in fact the residue curves. But we won't talk about them yet. All I want you to know is how we plot compositions. So the red dot is the composition we've just been talking about, and here's a green dot, which is a different composition. And this contains 0.2 dTBP. dTBP is a horizontal line that runs across that way, and it will start with high numbers near this apex, and it will have low numbers away from that apex. So this is exactly the same sort of thing as we had. How to plot a composition on a ternary diagram. Right, and that's as much as I want to go with the ternary mixtures. Now we're going to go back to binary mixtures for the rest of the lecture. Okay, let's talk about azeotropes. At this stage, I don't want to go into derivation and things like that. What I want you to do is to understand the graphs. You are probably very familiar with an XY graph. So if you've got a liquid at this composition, then the vapor, when you boil off the vapor will have this composition over there. The liquid is at this composition. Because this is where the x equals y, that's where the liquid was, that's the composition the liquid is at, and that's the composition that the vapor that comes off the liquid would be at. On a pxy diagram, here's your liquid composition. You go up to the straight line, and if you go horizontally at the same pressure, then that would be the composition of the vapor. So you go up to the straight line, move across, and there you get your composition of your vapor. And of course that you can plot back down, and it comes to the same point. Okay, so that's a XY diagram, a PXY diagram. PXY. And in this case, there's no azeotrope. This is a normal binary mixture that we're talking about over here. This is still a binary azeotrope. There's PXY, and there is an XY diagram, and so this is a very straightforward and common standard diagram. That if you've got a 50% benzene toluene, is it? Yeah, benzene toluene mixture, 50% benzene toluene, and you boil that off. At a certain, this is all at 90 degrees C. It'll boil at it'll boil at just less than 1 bar, and the vapor that comes off will have this composition over here, 0.7 benzene. So the benzene is the more volatile fraction. Similarly, we can do the same sort of calculation there, starting off with 0.5. When you boil it, the benzene that comes off will have a fraction of just above 0.7 in the vapor. So that means it's the more volatile fraction. Okay, that's pretty straightforward. This is the type of, well, I gave you TXY diagrams in the test. Okay, now we look at homogeneous azeotropes, and when we deal with azeotropes, we've got to take into account the activity, this gamma, and how it affects the liquid mixture. Usually you don't get much interaction in the vapor mixture, but we must use the activity of the liquid mixture. And usually that activity is greater than 1. In most cases, the activity is greater than 1, and the mixture has a minimum boiling azeotrope. So in this case, let's have a look at the pressure XY diagram. The pressure of the azeotrope is higher than the pressure of either of the two pure components. So the vapor pressure of the mixture is greater than either of the two components. If you look at let's go to the TXY diagram. That says that the boiling temperature, the temperature at which this mixture boils, is lower for the azeotrope than for either of the two pure substances. And this is a typical, this is what would happen with a water alcohol mixture as well. You will have the water alcohol will have a lower boiling than the alcohol alone. So this is not quite water alcohol, but isopropyl ether, but isopropyl alcohol, which gives a more prominent, more easy to notice azeotrope. And let's have a look at the XY diagram of an azeotrope. At low mole fractions of the liquid, it behaves as a normal thing, and the more volatile component will come off, and that will give you the, let's say we start at 0.5. The more volatile component will have a composition of 0.65, so 0.68. But as we get to much higher concentrations, if we've got isopropyl ether at 80%, and we boil it, the vapor has exactly the same composition because those two dotted lines are together. The vapor has exactly the same composition as the liquid that you're boiling it from. And if you start with 90%, then you find that the vapor, what was previously the more volatile component, is now the less volatile component. So you started with 90, and the stuff that boiled off easiest previously has now got a lower composition than the stuff you started with. So you invert the volatilities. Okay. What's also interesting, remember when you did distillation, that you've got an operating line that runs across here. If you've got total reflux, your operating line runs on the XY line, and then you can have your stages. You can put stages up like this. And the important thing is that you get an infinite number of stages as you reach this pinch. And therefore, this is a distillation boundary. So this point where the two curves cross is a distillation boundary. Therefore, this is a distillation boundary. And on a TXY diagram, that is a distillation boundary. So on the TXY diagram, let me explain what it would mean over here is that you can distill to that pure component and to that azeotrope in a perfect distillation column. If you start with a feed that is over here, you can distill to that perfect component over there and to that azeotrope. Right. So that is the definition of a distillation boundary. It means when the azeotrope doesn't allow any more separation. Right, and then if gamma is less than 1, you have a maximum boiling azeotrope. Maximum boiling azeotrope is best seen on a TXY diagram, the maximum temperature. It's got a higher temperature than either two pure components. So that would be an example would be acetone and chloroform. These are less common azeotropes than the minimum boiling azeotropes. Okay, I expected only to get this far in the lecture. Okay, but let's go through this thing. This is quite important, and it can be difficult to understand. So this is a TXY diagram, and there is obviously an azeotrope. That's an azeotropic composition. And because it's a TXY diagram, it's a minimum boiling azeotrope. That means if you've got a feed that goes into this distillate that goes with this solution, you would be able to distill this feed to make pure components of that composition and an azeotrope of this composition. But you can't get a product out of that distillation with that feed that ventures into this side of the dotted line. If you've got a feed that lies on this side of the dotted line, then you'd be able to make that pure component and that azeotrope. Right. So let's say that this is at a constant temperature. As soon as you've got a TXY diagram, you've got temperature on the y-axis, and therefore we're talking about a constant pressure. Let's say that this pressure happens to be 5 bar pressure. Then this temperature would lie at this point. Now these two, as you bring the temperature down further from this point, and you cool the pressure, at one temperature you will start to get a separation of two liquid phases. So at this temperature, you will get a liquid that has this composition, and the other liquid that forms has got this composition. So remember that separating flask that I've drawn in the past. I'm going to try and draw it again. Looks like a carrot. and it's got a valve at the bottom, and you can open this valve. Oh, that's supposed to be a straight line going downwards. Okay, so there's liquid in this. You've got your liquid mixture that's got this composition, and now you cool it down. There's your liquid level, and you cool it down, and what happens is it forms two liquid phases. So let's call it an aqueous and an organic liquid phase. And the aqueous phase is usually at the bottom, and the organic phase is usually at the top because it's usually less dense. And then you'd be able to open this valve and take off the water and measure its weight. And this water will contain some of the organic, and the organic will contain some of the water. So let's go back to this diagram here. I'm going to draw a line, shapes, line. I can still use blue, and we draw a line that starts over here and runs across to there. So it will be a horizontal line because it's all at the same temperature. And this point over here represents, let's say, the composition of this aqueous phase, and this composition represents the composition of the organic phase. So as you cool it down, and you get another line, am I still on line? Yes. As you cool it down, you get a sharper separation. In other words, this becomes more aqueous and this becomes more organic. Right, that brings us now to this second diagram. If instead of running, remember I said it, let's call this constant P 500 kPa, 5 bar pressure. Therefore, the boiling point of the azeotrope is high. If instead of 500 kPa, we draw a diagram at 100 kPa, the boiling point of the azeotrope and of the pure components will drop on this diagram. And as this azeotrope boiling point drops, it will intersect with this liquid phase envelope. And as soon as they intercept, you get this sort of thing happening. Okay, so if you've got a feed that goes into this system and the temperature is low, you will have a composition of aqueous phase that looks like that, and you'll have a composition of organic phase that will look like that, and you can make your separation. Once you've made that separation, you can use it as a feed to a distillation column that takes you into this region. And if you put this feed into a distillation column, you'll be able to make this pure product over here, and you'll be able to make that pure product over there as the two products from your distillation column. Yep, let me see what's this. When you're pointing with a pencil, thank you. Okay, so you've made this. I have to remember to go back to my pointer once I've used the line tool. You've made the separation. You started with this as feed. You've put it into one of these liquid separators, and therefore you can make a feed that looks like this that you can put into a distillation column here. That you can distill to that pure component and this azeotrope. On the other hand, with this feed going into this distillation column, you can make, oops, now I must go back to my pointer. There we go. You can make that pure component, and you can make that azeotrope. So I'm going to see if I can easily get to a whiteboard. But I still want that diagram on the whiteboard. No, I think I'm going to draw over here. So what we've got is a decanter. A decanter. Yeah, the question is, can't you do this with a heterogeneous azeotrope? If you make those two, can't you get back to that point? And I don't think you can, because you would have to be at exactly the right temperature, and it will not easily. If you go slightly above that temperature, then you'll lose your two-phase thing. So you can't. Pointer. Damn it. Okay. So the question, I think, if I interpret it correctly, is that can't you use this separation, this liquid-liquid separation, to achieve the same thing, rather than going to a distillation column there and a distillation column in this way and a distillation column in this way? And I don't think you can, because you can't get to that point. So once you, yes, did somebody? Your sound is really bad.
Would be homogeneous on the left.
Yeah, Louis. Could you hear that?
I think what Gabby's trying to ask, sir, is can you do the same type of liquid-liquid separation followed by feeding into two distillation columns for the homogeneous system as well? So can you split the liquid-liquid and then feed those two for the homogeneous case on the left as well?
Ah, yes. Yes, you could. Yes, you could. Absolutely. So let's go back to a line, a red line. So you can take it down to a low temperature, feed there, and feed this one into there. Yeah, absolutely correct. Yeah, but then why would you want to go up to 500 bar? Because remember, we were talking that typically you find easier separations happening at lower pressures. So yeah, the liquid-liquid phase envelope is not affected by pressure. So you would always want to, you would prefer to operate your distillation columns at a lower pressure. You can see that these lines are further apart here at the lower pressure than they are at the higher pressure. And so it makes the separation a little bit easier. But yes, you could absolutely. So anyway, the point I was getting to when I was trying to draw, let's use green, is that you would use a decanter. A decanter is a piece of equipment that you would use to do this, the liquid-liquid separation. And from the decanter, you would have two distillation columns. From the decanter, you'd have a product coming off, which is the organic product, and the liquid product. This one would go to a distillation column, and this one would also go to a distillation column. That's just the line. There's a distillation column, and each of these will have products. This is so difficult. Right, each of those has products, but now that's the high boiling. Let's look at this one. That's the high boiling one. That's the low boiling one. The low boiling temperature. So the azeotrope is always in virtually all of the cases, you have a low boiling azeotrope, and therefore the azeotrope tends to come off. Oh, I didn't have my pointer going. There's the low boiling part of it. If you take this distillation column, there's the high boiling part. That's going to be the bottoms of your distillation column, and this will be the distillate. And the same applies over here. The pure components at the bottom. So here is the pure component of this distillation column. That's the pure component of that distillation column. And what you get coming off the top is exactly the same composition. There's the same composition as coming off at the bottom, both of the at the top of both of these distillation columns. Therefore, let me get back to the pencil, and I'm just going to change the color. Therefore, this azeotrope that comes off here, we can mix with that azeotrope that comes off there, and we can put that back. We can put that back into the decanter. So once we've done this and we get an azeotrope, we mix the two azeotropes from the two distillation columns, we decant, and we can get back to the separation that we wanted. So what we're doing ultimately, this is going to mix with feed. So the feed is coming in here and mixing with this recycle. So the feed has got the two components, that component and that component. And ultimately what we're getting out is those two components as pure components coming out over there. So you can see how having a diagram, pointer, having a diagram like this, it gives you information about the azeotropes and the liquid-liquid phase envelope. And from there, you can do process synthesis, because you know that the first thing you'd want to do is the liquid-liquid extraction. Once you've done that, you will have two different compositions that you can easily distill to make pure components. Those pure components have got a higher temperature than the azeotrope, therefore they both come out at the bottom of the distillation columns. And those compositions coming out at the top of those distillation columns are exactly the same composition. And you could recycle that. And if you mix it with the feed, let's assume the feed has got the same composition there, you mix it with the feed, you're essentially back where you started. And ultimately you have separated the one component from the other. Those are two pure component streams, and you've achieved what you need to achieve. Okay, so I don't want to go further than this. The next bit will be understanding residue curves. So let me take some questions now that we've reached this point. Yes, Jacques-Louis.
So this decanter, are there continuous versions of it? Because I only kind of know of a batch type where you have them settle and then take off the two. Are there continuous versions of this?
Yes, they are. I'm just gonna let's close this, navigate slides. So I'm just trying to get to a whiteboard. Share files, share blank whiteboard. Right. I have shown you this in class before, but let me draw the let me draw the decanter that in this way. Then a line that looks like that. And then a stirrer. And then here's your feed. Okay, so this feed you would put through a heat exchanger to cool it down, because then you will have two liquid phases. Here you would mix, or you could have two different compositions that are coming in there, and that's why you'd want to mix them to get to a chemical equilibrium, phase equilibrium of the two liquid phases. And then that liquid goes out over there. At some point, you're going to have a liquid level. This is let's assume that there's vapor on the top there. Let's even put in a vent that is atmospheric. Because remember, this liquid thing can operate at any pressure. What's going to happen is that when you mix it, you're going to have one of the two phases is going to be a discontinuous phase, and the other one will be a continuous phase. So there are a whole lot of bubbles. And let's say that the bubbles contain the aqueous phase, the organic phase, and the continuous phase here is liquid. Ultimately, as this stuff moves along in this direction, the bubbles are going to rise to the surface because they're the organic phase. So now I'm going to go back to the pencil, and you're going to find a concentration of the bubbles up near the top. As this mixture moves across in the decanter, eventually you land up at the end, and you get a phase separation occurring as these bubbles coalesce. And you can take off your organic phase over here, and you can take off your aqueous phase over there. So how do you make sure that you have your phase separator at that point? Is you will have a control system that measures the pressure. You measure the pressure over there, which measures the density, the average density above this point, from there to there. So if you measure the average density, you must just make sure that density, let's say organic is a 0.8. I'm just going to use the text tool. The organic has got a density and the aqueous has got a density of 1. If you measure the pressure there, and you know the height between this point comes off over there, you know the height up to the top there, and you're measuring, let's say that the dP, maybe it's dP that you should be measuring across that, from that point to that point. If you control this flow rate, if you take off more water, then this interface will actually move downwards, and the average density will get less where you're measuring this pressure. So you'll measure a lower pressure. And I'm talking about a rho GH pressure that occurs across that point. And so you simply have to control this pressure to be such that the density equals about 0.9, somewhere between these two densities. That will ensure that you're controlling that interface stays between the two offtakes. Right, let me see on the chat what was the last questions. Just to be sure, for heterogeneous azeotrope, is at that point will there be 4 phases? No. No, there won't be 4 phases. I wish I could go back to that slide. Let me rather just draw it. Let me just see if the share files have still got that. Share now. Yeah, there'll only be 2. When the temperature is above this line, so if whatever your stuff is that you're talking about, whatever the composition, anywhere above this line, you will only have the 2 phases, and those 2 phases are going to be liquid and vapor. So you could have only liquid at its boiling point, but anywhere above this temperature over here, you will have just a single liquid phase. So either it's going to be something at liquid at its bubble points at that temperature, and then you only have liquid, and as soon as you start boiling it, then you'll have vapor as well. So above this temperature, 2 phases, liquid and vapor. Below this line, 2 phases, and both of them are liquid phases. Let me just see. Homogeneous azeotrope again. The homogeneous azeotrope again. Look, this is exactly the same as any normal azeotrope. We've got a low boiling azeotrope. If you've got a feed that comes in at this point, you can distill to that pure component, and you can distill to that azeotropic composition, but you can't do anything else. Feed at that point, well, even if you cool it down, it's possible you can get to 2 liquid phases down there. If you've got a composition that starts at that point, you can distill to there, and you can distill to the azeotrope. Esmarie, talk to me. Do you understand it better now? Oh, good. Thank you. Phew, well, that does take us to 20 past. So I was accurate in only wanting to get to this slide, but it is a difficult slide. But we will be doing liquid phase separations as part of the ternary diagrams as well. And so it's good to just get an introduction to liquid separations at this stage. All right, guys, I'll see you again next Monday, and then we can do a very important lecture, and that's going to be understanding residue curves. All right, thanks very much, people. See you Monday.